Hello, everyone. We'd like to introduce you to Schrodinger's Vault. I'm Anthony Brunetto.
I'm Shay Gallagher.
I'm Adrian Pablo Garcia.
And I'm Vincent Palma.
Our objective was to build a fully local desktop password manager using quantum-resistant libraries and algorithms available for Mac OS, Windows, and Linux. Quantum computers will soon be able to break much of the encryption protecting today's password managers. Attackers are already collecting encrypted data now to decrypt later once quantum resources are available, making quantum-safe encryption an urgent need for governments, companies, and users alike. We wanted a password manager that's accessible, open source, and secure against this threat. With open source done right, the community can strengthen the software over time instead of relying on security through obscurity.
Our app is named after Erwin Schrodinger, known for the famous Schrodinger's cat thought experiment. The core idea is that the cat's condition remains unknown until the box is opened. We use that concept as a metaphor for our vault. The data inside stays completely inaccessible and unknowable to anyone until a user unlocks it.
Our application is built with Tori, using a Rust backend and JavaScript frontend. We chose Rust because its strong memory safety guarantees help us prevent mishandling sensitive security data. The system implements post-quantum algorithms selected by the National Institute of Standards and Technology to protect user information against future quantum attacks. We go beyond typical password managers by adding multiple layers of security, a master key that is never stored in memory and is reconstructed on every unlock, a device-unique secret stored securely outside the vault so stolen vault data can't be decrypted elsewhere, and per-entry encryption, where every password is individually encrypted and stored as ciphertext. All sensitive data is zeroized on lock, idle, or exit, ensuring cryptographic keys cannot be recovered after use. Our cryptography uses FIPS-compliant algorithms, making the system suitable for government-level requirements. Finally, the project will become open source, allowing community review, transparency, and continued security improvements.
NIST has finalized the first generation of post-quantum cryptography standards, and our vault is built on these federally approved algorithms. This matters because RSA relies on factoring large integers, and elliptic curve Diffie-Hellman relies on discrete logarithms, problems a quantum computer could solve using Shor's algorithm. As a result, data encrypted today may not remain secure in the near future. For secure key exchange, we use MLKEM 768, the NIST FIPS 203 standard. MLKEM is quantum resistant because it uses lattice-based techniques. Lattice cryptography uses algorithms that create large, grid-like structures in multiple dimensions, and there are currently no quantum algorithms developed to solve them. Unlike previous classical systems, quantum computers don't gain any advantage in breaking quantum-resistant algorithms. This allows us to establish shared secrets that will be resistant to post-quantum threats. For digital signatures, we use MLDSA 44, the NIST FIPS 204 standard. It is also lattice-based and avoids the structural weaknesses that make classical signatures vulnerable to quantum attacks. MLDSA provides a reliable method for verifying authenticity and integrity of vault metadata and stored entries. Together, MLKEM and MLDSA create a cryptographic foundation that aligns with federal standards and maintains security as quantum computing continues to develop.
Originally, we planned to let users choose between Aragon 2ID and PBKDF2 for key derivation. Aragon 2ID is faster and generally considered the stronger modern algorithm, but it is not FIPS compliant. Since FIPS compliance is required for government-grade security, we shifted to using only PBKDF2, which meets US government encryption standards and ensures broader real-world applicability. For storage, our plan was to use pure SQLite, but that would have required writing low-level C code, manually handling memory, and implementing many database features ourselves. To avoid unnecessary complexity and improve safety, we switched to RustQlite, which provides a secure, high-level Rust wrapper around SQLite while still giving us full control over the database. On the front end, our initial idea was to place all of pages into a single HTML file with one JavaScript file for all of them. Once we started building the project, we realized this approach would quickly become difficult to extend, so we switched early to a multi-page structure, giving each page its own HTML and JavaScript files. This made the layout clearer, easier to understand, and more maintainable from the start.
On vault creation, the app generates a random salt and uses a key derivation function with the user's master password to derive a key K1, which encrypts a small fixed value stored in the local database. This enables the password to be verified without ever being stored. The system also creates extra salts and a device-stored secret using a post-quantum key encapsulation mechanism, and saves only the public key and ciphertext in the database. To prevent tampering, it builds a manifest of important metadata that is then hashed and signed. All sensitive keys are kept in memory or secure storage and wiped right after use. On future logins, the app uses the user's master password along with the stored salt to rederive the K1 key. If the password is correct, the app rebuilds a manifest of critical metadata, hashes it, and checks that this hash matches the stored hash and a valid signature. The unlock attempt is blocked if the match fails. Next, it recovers a shared secret by decapsulating the stored ciphertext with the device's private key. And finally, K1 and the shared secret are blended to derive a vault key, which is stored only in memory for the duration of the session, while K1 and the shared secret are zeroized immediately after use. If verification is passed, the user is presented with their vault of entries. When an entry is added, the plaintext password is encrypted using the in-memory vault key. A fresh nonce and authentication tag are made for every entry and are stored with the ciphertext in the database. The plaintext buffer is wiped immediately after encryption so nothing sensitive remains in memory. The UI then updates to display the new entry. When an entry is deleted, the backend wipes the encryption record from the database. All sensitive data stays encrypted in storage and decrypts only when the user explicitly views or copies a password. If the user wants to view a password, the app temporarily decrypts it using the vault key. After decryption, the plaintext password is revealed for a 10-second window. If the user chooses to copy the password, the same decryption occurs and the resulting plaintext is written to the clipboard. A timer clears the clipboard after 10 seconds to minimize exposure.
The next phase is locking the vault. The vault locking step is responsible for wiping the AES vault key and clearing the contents of the clipboard. This ensures that sensitive information about the user is no longer accessible once the application is closed or locked. The vault locking process occurs when the application is closed by the user, when the user leaves the application idle for 5 minutes, when the lock vault button is pressed, and in the event of a crash. Once the vault is locked, the memory containing the AES vault key is zeroized. Zeroization is the process of erasing data by overwriting it with junk values, usually zeros, to make it unrecoverable. This ensures sensitive information such as passwords and the master key only exist when they're in use of the application. Part of our verification process was making sure our implementation of memory zeroization behaves as expected. We do this using the GNU debugger tool to inspect memory containing sensitive information as we step through the program. This is an example of wiping the AES vault key derived from a dummy password. Once the breakpoint is hit for the zeroize AES key function, we inspect the vault encryption key. The vault key is stored in a Rust container called an RW lock, which lives for the lifetime of the application. By examining 32 bytes as unsigned integers at the memory address of the RW lock's data field, we see the same key as the previous slide. Inspecting the memory itself verifies zeroization occurs as expected and no hidden references to the data exist. We then step past the zeroization step. Printing the RW lock's contents displays a none in the data field rather than the original vault key. When examining memory at the same address, only junk values remain, confirming the AES key has been wiped. This process of memory zeroization verification was done throughout the application to make sure sensitive information created and used throughout its lifetime is no longer accessible once it's unneeded.
During this project, our biggest technical growth came from learning Rust, since most of us had only used C for low-level programming. We also worked in the Tori framework, which let us build the application using a JavaScript frontend and a Rust backend. Another major skill was applied encryption. Instead of only studying theory like we have only done throughout our classes, we actually implemented real encryption flows in a working system. We used the GNU debugger to inspect low-level memory and verify that our application handled sensitive data securely. We also wrote Rust unit tests to confirm all zeroization logic, ensuring password, keys, and shared secrets were wiped from memory correctly. In addition, we configured Open Quantum Safe, or OQoS, to support quantum-resistant key generation and secure storage. Beyond the technical side, we improved our project documentation and tracking, keeping detailed logs of issues and solutions for our future research paper. We also practiced team communication by giving weekly updates to our mentor. Finally, this project strengthened our goal-oriented planning, since unlike typical class assignments, we work through long-term milestones and iterative objectives.
Moving forward, we plan to refactor the code and create in-depth documentation. We also want to add support for Argon 2 ID so users can choose the preferred encryption method. Another major step is building an installation wizard to automatically configure dependencies like OQoS and OpenSSL. Eventually, we aim to release the final developed project as open source. Schrodinger's Vault will be published at the CrossSec conference in Portugal, April 2026. Our download link is still in progress at schrodingervault.com/download, but visit and download our open source dev repo at evolvingcyber.com/open-source.
Lastly, we want to say a special thank you to our mentor Aisha Lally, who guided us the whole way and gave us great support. We also wanted to say thanks to our capstone professors, Boot Sue and Paige Weiskirk, and we want to say thank you for watching.